So today I want to introduce the Euler kernel, and then we'll talk about integral representations for the hypergeometric functions. I'm saying integral representations as opposed to just integral representation because I'm going to show you how the choice of contour on the integral will determine the representation. So the hypergeometric function is a solution to the hypergeometric equation, and as such, the hypergeometric equation is a second order differential equation. So I'm expecting 2 billion independent solutions. So I should be able to show you at least 2 of them. We've already written them down. Today I want to show you how we determine those of the integral representations. Okay. Very good. So there's a lot of kind of tedious detail that I'm leaving out from this lecture just because it really is tedious and it will take up a lot of note space. But it's just taking derivatives of polygons, right? So you guys do that in your sleep. I don't really need to say much more, but what I am going to do is guide you to what type of differentiation. Okay. All right, so let's recall what it is we're trying to do. Essentially, we're studying the operator Lz equal to z times z minus 1 times z times 1 minus z 2 z squared plus gamma minus alpha plus beta plus 1 times z z minus alpha times beta. Now what we'd like to do is solve the differential equation Lz acting on some function, let's say u of z. So we want to study solutions of Lz times, so acting on uz. So we would like to explore the properties of these solutions, hopefully not by having to actually solve the differential. Right, so I've already motivated where this differential equation would arise, for example, so take the excitations of molecules. I've hopefully shown you how, as solutions of the Cauchy-Taylor equation, you have these hypergeometric functions, and they have these interesting properties, and you use these properties to deduce the eigenvalues, to deduce the energy eigenvalues of that particular system, right? So all of this is super interesting, and I kind of gave you an historical account of where the origins of quantum mechanics, etc. But these are still cutting edge problems that came this morning, in fact, or yesterday, that was exploring the Cauchy-Taylor quantum mechanics problem. There's a new technique that was developed over the last couple of years called quantum bootstrap. So basically, given some minimal data about some quantum mechanics problem, can you use the solution of the quantum mechanics problem numerically typically? And the Cauchy-Taylor system is one such system that you can benchmark these new methods against when you try to go to higher problems. Okay, so this is all still cutting edge research, even though a lot of what we're talking about was done decade. All right. So we would like to study solutions of the equation LZ and UZ. First thing to note is that in writing down an integral representation, we would like to write it down in the form u of z equals some integral of some kernel times some function b of z, right? That's the game that we're playing. And we're hoping that with an appropriate choice of kernel and appropriate concept of integration, we can write down an equivalent system that we need to solve for b of z, like you did when you were studying the problem using Fourier transform. And that will be a simpler problem. You solve that simple problem, you learn how to invert the integral, and then you can write down the solution. Okay. Okay, so that's the goal. And the first step in this in realizing this goal is to pick a kernel. Right? Now, you know how I said to you before, anybody can differentiate that integration is an option. If I didn't tell you, integration is an option. The reason for that is because there's no algorithm for how to integrate. You learn some of the basic tricks every now and then, but if I throw an integral at you, you really have to basically just stare long enough and hope that these tricks that you've learned can show you a way to. The more integrals you do, the better your intuition, the easier it is to solve it. In the same way, picking a kernel is an option. And really, the choice of the operator dictates for you, but it doesn't give you an algorithm. It dictates for you what kind of kernels you should do. Right? The more problems you do like this, the more intuition you build, the easier it becomes to pick the kernel. Picking the kernel is one big step in solving the problem. So in this case, the kernel depends on what these coefficients functions are. Right. So here I have polynomial coefficients. Okay. And the fact that I have polynomial coefficients tells me that I shouldn't go looking for exponential kernels like Fourier. They're not going to help me in this case because of these polynomials. But if I can find a kernel that has a polynomial structure in S and T, right? S being the transform variable, T being or Z, I guess, being the problem here. Solve here, Z and T. Then maybe that will make my life easier. And in fact, one such kernel does exist. It's called the Euler kernel. So, since the coefficients of LZ are polynomial, we can choose for the kernel function, we'll choose the Euler kernel. Euler kernel function k of z t equal to z minus t to some power s. Okay, this power s we'll determine a little later, explained by the differential equation. But essentially, this is to be determined. Okay, so this kernel here, z minus t to the s, is called the Euler kernel, and you'll notice that it's not the same structure as we've been working with Fourier and the past kernels, but you'll see how this is going to help us solve the problem. And then remember, what happens inside the integral is this operator Lz acts on the kernel, right? This is the second order differential operator. It's going to act on this kernel, and this is why I've chosen the polynomial kernel, because differentiating this polynomial then just keeps putting down factors of s, right? So I'll pull out two factors of s, or pull out a factor of s times s minus 1 from the first term, I'll pull out a factor of s from the second term, and then I'll have a bunch of s's and gammas and alphas and betas, and I'll have to organize them. So I'm going to leave out those steps for you guys to fill out. So acting then with LZ gives the following. LZ on K of ZT. So what I've done here is I've acted with each of these terms in the differential operator, and then I've repackaged my result so that I organize in powers, descending powers of Z, and I'll pull out any power factors. Okay, so when you do that, you get as coefficient of Z squared minus S times S minus 1 minus S times alpha plus beta plus 1 minus alpha beta. So these are all coefficients of Z squared. That plus coefficients of Z. I have S times S minus 1 plus S gamma plus S times alpha plus beta plus 1 times T plus 2 alpha beta T. Then as coefficients of 1, I have minus gamma ST minus alpha beta T squared. All of that multiplies the common factor that I'm pulling out of S minus T to be S minus 2. Z minus T to be S minus 2. So fill in the gaps here. This is how this is changed. Okay, so again, let me remind you of our strategy. We're going to act on, so recall that we want to write this guy as the integral of K Z T B T dt for some contour on this T plane. Right? And then when I act on U with LZ, it only acts on K. That's what we've discovered. Okay. And then what I'm going to do is I would say, suppose there's some operator M sub T, right? Differential operator acting on T variable, such that LZ on K is MT on K. And then I find the conjugate of that by integrating by parts. And that conjugate differential equation is what I want to solve, and I'm hoping that it is a simpler equation to solve than the original. Okay. Okay, so the question is, how do we choose? How do we choose this? Operator MT. Okay. And just in the same way that we saw that saying, well, because I've got polynomials there, it makes sense to pick a polynomial panel. There's a similar intuition that applies here with MT. So notice the following. Remember the difference between this M operator and the L operator is that M is acting on the T variable, right? And L is acting on the Z variable. But if I look at my kernel is nearly symmetric. Right? Notice that K of T and Z, if I exchange T and Z, is nearly the same as K of Z T. Except for the factor of minus 1 to the S. So depending on what the S is, which again I have to constrain for the differential equation, this kernel is nearly symmetric, right? It has some solution. Right? and this is the symmetry. So the fact that it's symmetric almost with t and z variables tells me that if I'm going to choose an operator that's going to act on it, right, act on the t variable in such a way that this operator acting on in such a way that mt acting on k is the same as L acting on k, then the structure of M and L must be similar. Okay. So this gives me a clue as to how to pick the operator MT. Namely, that MT should have the same form as LZ, except possibly with different coefficients. That's what I need to solve. Okay. So we're going to choose MT. This is just a definition as some coefficient, which I'll call P2 T. P2 will be the coefficient of the second derivative. Plus T1 T will be the coefficient of the first derivative. I'm going to not choose a constant coefficient in the hopes that that will make things a little easier. This might end up being inconsistent, in which case I'll find out shortly. Right? But if it's not inconsistent, then I can actually solve for the p's in terms of the alpha, beta, and gammas associated to LZ. Then I will have solved the problem of making it a little bit simpler in the t space. Okay, so notice no constant coefficients. And I'll add that this might still be inconsistent. We will find this out. And the inconsistency will manifest in not being able to solve for the coefficients. Okay. But if I can't solve for the coefficients, then I'm good. Okay. So now we want to apply MT to K and equate it. So if I do that, we will find the following. That S times S minus 1 times P2 T minus P1 of T times S times Z plus P1 of T times S times T plus equal to all this stuff. Full stop. I don't really want to write that. Okay. So you see now why I have organized everything in powers of Z here. Because for this to hold, for this thing to be equal to everything in here, they have to hold, I have two polynomials in Z. The only way they're going to be equal is if the coefficients are equal at each order z, at each power z. Yeah. So this solves if there are only two things, well, three equations. Firstly, at order z squared minus s times s minus 1 minus s times alpha plus beta plus 1 minus alpha beta is 0. At order z, minus p1 times s is equal to s times s minus 1 plus s gamma plus s times t times alpha plus beta plus 1 plus 2 alpha beta times t and at order 1 s times s minus 1 p1 oh sorry p2 plus s t1 is equal to minus gamma s t minus alpha beta t squared. Okay. This first equation requires that either s is minus alpha or minus beta. If s is minus alpha, then the left hand side is equal to 0. If s is minus beta, the left hand side is equal to 0. And you can see it's symmetric in alpha and beta. Right? So this means that either s equals minus alpha or s equals minus beta. It turns out that both of these will give the same representation. It doesn't really matter which one we choose, but let's just pick s equals minus alpha for definite percent. So if I choose s equals minus alpha, that allows me to solve the remaining equations, which are two equations and two unknowns, p1 and p2. So it's consistent. Right? So choosing s equals minus alpha, which solves the first equation, gives t1 t equal to alpha plus 1 minus gamma plus beta minus alpha minus 1 times t and 2 of t equal to t times 1 minus t. This is the 6 steps here, which is just solving two linear equations for unknowns. Difficult, but what we get at the end of the day is that our operator t is then t times 1 minus t, 2 t squared plus alpha plus 1 minus gamma times beta plus beta minus alpha minus 1 t d by dt. Okay. Good. So now we're in a position to calculate the adjoint of this thing. Remember, we're going to calculate the adjoint by looking at the integral mt acting on some u of t times d of t, and then integrating by parts. Okay. Second derivative here, if I move this second derivative onto the v, I'll pick out 2 minus signs, so there's no sign change there, and there's a sign change that comes with this first derivative term. But essentially, what will happen is after you integrate by parts, I'm going to assume that all the boundary terms can be accounted for. The remaining operator on the right hand side will just be m diagram. Again, I'm going to leave these integration by parts steps for you to do. The resulting differential equation is that d2 by dt squared on t minus t squared times v minus d by dt on alpha minus gamma minus gamma plus 1 plus t times beta minus alpha minus 1 all multiplied by b. This is the adjoint differential equation. That constitutes the adjoint problem that we need to solve. Okay. Believe it or not, this problem is actually easier than the problem we started off with. But I'm not going to ask you to solve it. Rather, I'm going to give you the answer and I'm going to ask you to check it. I want you to do two things. Firstly, by expressing this second order equation here as a second order differential equation in V, right? So in integrating by parts here, I didn't really finish the integration by parts, right? I just pull out this t times 1 minus t term multiplied by V. Actually do the differentiation. And I want you to check that a solution of the second order equation for b of t is that b of t can be written as some constant times t to the alpha minus gamma times t minus 1 to gamma minus beta minus 1. That's point 1. Secondly, I would like you to show that the boundary term, the boundary term that we dropped in this integration by parts. Remember, there was this q term that came with the boundary, and it required the q term to vanish as well. I want you to show by properly doing the integration by parts and accounting for that boundary term, the boundary term in the integration by parts is Q of A and V equal to constant alpha T alpha scalar minus 1 times T minus 1 to gamma minus beta times T minus alpha 1 on this solution. In other words, I will get an expression for Q in terms of K and V from the integration by parts directly. I will then substitute this V into that, and I will get this. So that's what I want to show. Okay. All right. So that's the exercise. So now I need to specify an integration contour. Remember, what I'm trying to do is write out my solution as something like this. Right? This integration contour C, sorry, I apologize for calling it C. The integration contour is important in determining this representation. So now we need to figure out what's a good integration contour to choose. The point here is that different integration contours will give us different representations. But either way, the contours that we choose must have that this Q must vanish, and this is the reason I'm asking you to find it. This Q must vanish. Okay, so I have two options here. Either I can choose a closed contour. If I choose a closed contour, then there's no boundary, so there's no boundary condition. So this will necessarily be 0. That's how I'm choosing Q. Or I choose an open contour in which this Q is the same on either end of the contour. Okay. So we now need to choose a contour called curly C with vanishing Q. So we have two options. If C is closed, Q is necessarily 0 because it does C has a boundary. 2, if C is open, we need Q to vanish on its boundaries. Okay. So now let's go to this expression for Q. And I want you to notice the following. First point is that if the real part of gamma is bigger than the real part of beta, the real part of gamma is bigger than the real part of beta, then as t goes to 1, q goes to 0. Okay, I mean, the easy way to see this is imagine gamma and beta are both real numbers, and if beta is bigger than gamma, then gamma minus beta is a negative number. As t goes to 1, this goes to 0. Sorry, gamma is bigger than beta. So this is a positive number. T goes to 1, this goes to 0. Okay. So if the real part of gamma is bigger than the real part of beta, then Q goes to 0 as T goes to 1. Technically, T goes to 1 on the right. On the other hand, if I ask what happens to this function as T goes to infinity, then notice that Q goes to, basically, I'm asking what happens to this function of T as T goes to infinity. Q goes to -1 to the minus alpha minus 1 times constant times alpha to the T, so alpha times T to the alpha minus gamma plus 1 times T to the gamma minus beta times T to the minus alpha minus 1. So basically what I'm doing is I'm making the expansion in 1 over T, this, and then I can add up all the coefficients, add up all the powers of T, and I'll find that this is equal to -1 to the minus alpha minus 1 times constants, C times alpha. And the only remaining power of T goes like minus beta, which goes to 0 if the real part of beta is positive. Okay. So again, let me recap. We worked out what the boundary term is. Right? Our choice of contour is going to have to be such that the boundary term vanishes on the contour. Either the contour is closed, in which case the boundary, there's no boundary, nothing to worry about, or the less trivial case is if the contour is open, in which case I explicitly require Q to vanish on the endpoints of the boundary. So now I'm trying to work out what my contour must look like by studying this function Q. So I'm picking a contour such that reverse engineering the problem, Q vanishes on the endpoints. Right? What we've discovered is the structure of Q is such that if the real part of gamma is bigger than the real part of beta, then Q vanishes as you approach 1 from the right. When you approach infinity from the left. So essentially, by studying the structure of this function near close to infinity, I'll find out that it vanishes provided the real part of beta is positive. So now this gives me a constraint. If the real part of beta is positive, but less than the real part of gamma, I know what to do. Pick the contour on the T-plane that goes from T equals 1 to infinity. That's enough information to tell me that if I choose a curve from T equals 1 to infinity, with the assumption that the real part of gamma is bigger than the real part of beta, and both of them are positive, then I can write so if I choose a contour going from T equals 1 to infinity with real part of gamma bigger than real part beta both positive, then I can write